everyone, I'm Dr. Meena, Assistant Professor, Department of Mathematics from KPR Institute of Engineering and Technology. In this video, I am going to present how mathematics are applied in the field of cryptography. So, cryptography is nothing but it is a science of information that transfers the information from a plain text into a ciphertext. So cryptography is nothing but a combination of encoding as well as a decoding. So everybody knows, so in this encoding as well as the decoding, based upon this only, we can able to transverse the data from a plain text into a ciphertext. And once again from the ciphertext, it is transformed to the plain text. So here mathematics forms the backbone of this cryptography. Mainly the mathematical concepts are applied in all these transformation. So the first thing is we are going to see how mathematics actually do in cryptography. So basically in mathematics, in modern algebra, we are having four important concepts in groups. One is the closure property, another one is the associative, identity, and inverses. So even the school children know about these four properties which are very applied. It is very important. It is used in modern algebra. So, but we don't know how it is really applied in cryptography. So this closure, in this property, we can see the operations stay within the set. In associative, the order of the operations is not the matter. It can be changing in order. In identity, we can see the neutral element exists, and in inverse, we can see every element has the opposite element. So combining all these four concepts, this cryptography converts the messages into an algebraic elements by transforming the plain text into a structured mathematical objects. So these are the very important axioms of groups. So cryptography lives naturally inside the group theory. The next thing is we can see here the group theory acts as the language of the cryptography. So what are the encryption requirements and how the group properties are applied here we can see in this slide. So the first one is the deterministic transformation. The deterministic transformation, one of the important concept applied here, it is structured composition. And the second one is reversible under the specific key, and absolutely we are using the inverse concept here. And the next one is unpredictable. That is, here we can see the closure property of operations are used here. So we can see encryptions becomes a group action. The next thing is we can see how we can use the rings and fields in cryptography. So once again, we can see the three main concepts. One is the addition, multiplication, as well as the distributive structure. So we know the addition and multiplication of the basic arithmetic operations, and in distributions, we can see some link operations also. So here we can see in that rings and fields, it is one of the important concepts in modern algebra. It allows a structured arithmetic with a bounded size. It ensures the finite computation, similarly periodicity, as well as no infinite growth. So the next concept we are going to see is about AES. So what do you mean by AES? Means it is nothing but an advanced encryption standard. So it is a symmetric key block cipher. It is standardized by NIST in the year 2001. And here this algorithm, it is designed by John Damon and Vincent Richman. So here it is mainly used in banking systems and in web security, Wi-Fi security, and in government communications. So in mathematically, AES is fundamentally built on finite field algebra. So without the algebra, we cannot frame this AES technology. So now we can see how this AES is mainly it uses the mathematical concepts here. So major four concepts are used here. One is the finite fields, another one is the linear algebra, then polynomial arithmetic, and then matrix transformations. So it is finite fields means algebraic structures. It will be with the limited elements. Another one is the linear algebra, that is the matrix operations and transformations. And the next one is polynomial arithmetic, that is operations on polynomial expressions. And then matrix transformations, that is the linear mappings between the spaces. So we can see these four main concepts are applied in this AES. So why fields are ideal for AES means here every non-zero element has multiplicative inverse. Similarly, it should be there is no zero divisors and it should be closed under the operations. So every non-zero element has a multiplicative inverse. This concept it is used as every transformation is invertible. So without a field, we can say inverses may not exist. Similarly, no zero divisors means here decryption as well as encryption, it is mathematically guaranteed. And in operations, stay inside a closed finite structure and the security is also maintained here. So in this way, AES uses the inverse operations, similarly polynomial multiplications and then matrix transformations also. The next thing we can see how the probability are applied in cryptography. So everybody knows the probability is nothing but it is a predictor. That is, we can predict something, whether it can be done or not. So the mathematics ensures that probability distributions behave predictably. So without the probability theory, we can say this encryption collapses. So some of the major concepts here which is applied here are it is number theory, abstract algebra, algebraic geometry, probability theory, and computational complexity. So one of the example we can see in is it is f to power 8. F to power 8, it means a finite field. It's containing exactly 256 elements. So all the areas we can say we can work under inside the field with exactly 256 elements here. Another example is we can see this digits, that is binary number 10110010. So here we can see how does a byte become a polynomial. So each bit corresponds to a coefficient, that is from left to right, and this becomes, or this polynomial is an element of f to power 8. So we can say this polynomial, it can be reducible or it is irreducible. Suppose if the polynomial is reducible, then automatically the quotient will contain a zero divisors. If whenever a quotient contains a zero divisors, it won't be a field. So a field, it must be a non-zero divisors. So we can see irreducible, it should be that polynomial, it should be irreducible. So irreducibility property is must here. So without irreducibility, there is no field. So AES becomes impossible. So in this way, in AES, a byte is not treated as a number, it is treated as a polynomial and it has a definite form. So based upon all these things, this AES uses the binary numbers and which can be applied in this encoding as well as in decoding. So based on all these concepts, we can see some, what are the things we can take away. That is, the one is AES manipulates the algebraic fields. AES is not a manipulating numbers. It is manipulating elements of a finite algebraic field. And the next one is, it is a security from mathematics. Security comes from the mathematical concepts. It is like an algebraic complexity, similarly non-linearity, as well as indiffusion. So normally the students will learn about the linear combination, similarly algebraic structures, then linear equations, non-linear equations, complex numbers, those things. So here all these concepts we can use in this security. So once all these concepts are applied in this cybercrime, so we can see how the encoding as well as decoding are applied here. So in this way, we can say the mathematics behaves as a backbone of cryptography. So without the cryptography, so we cannot able to do the banking work, and similarly cybersecurity, and then we cannot use the that is some information gatherings, transferring the informations, secret codings, transformations, and all these things. So in all the concepts we can see that is how mathematics are applied here. So basically I told you that is the cryptography is nothing but it connects the data so into a secure format using some advanced mathematics. It protects privacy as well as it is a technology which evolves. It remains critical to encounter the new threats. The future focus on quantum resistance algorithms. So the fundamental security services, it provides 5 core services: confidentiality, integrity, authentication, availability, and so on. Similarly, cryptography is crucial for securing the online communication and similarly protecting sensitive data storage and so on. So by this video, we can see how mathematics are applied and how mathematics behaves as a backbone of cryptography. Thank you for watching this video. Thank you.